Okay, so as I was saying, nonlinearity can be coming from the material, right? And there is another type of nonlinearity that can be coming from large deformations. Okay, so there were two major assumptions that we were making throughout the process, throughout this analysis course. One assumption was that material behaves linearly, and that was allowing us to do all kinds of superimpositions. You might have noticed along the way that we were doing a lot of superimposition. So where were we doing the superimpositions? Anybody remembers? Or anybody can suggest?
While we find the deflections of the things, superimposition.
Yeah. See, the thing is,
superimposing stiffnesses also.
Yeah, you are superimposing the stiffnesses also. Assembly of the stiffness matrix is not truly superimposition, if that's what you mean, Prithvi. But see, the superimposition is a very, very low, it is made out as if it's something very serious. But superimposition we were doing everywhere. So as soon as you write that equation, F is equal to Ks, or F is equal to SD, sorry, I'll revise it. F is the action or force or action. A is equal to SD. That was the sign convention we were using, right? Or the nomenclature. A was the force, S was the stiffness,
yes,
and D was the displacement. So A is equal to SD. As soon as you write that equation, you are assuming a linear behavior. And there is superimposition built into that one, isn't it? What does that mean? So if your A is half, your D will be half. If your A is twice the force, your D will be twice the displacement. Agreed? So that is superimposition. If you have A1 is equal to SD1 and you have A2 is equal to SD2, then automatically A1 plus A2 will be equal to S multiplied by D1 plus D2. So as soon as you write that equation, all these things automatically become true. So that equation itself has the superimposition built into it. You follow me?
yes,
Yes,
sir.
sir.
Okay, so we were making that assumption. So that equation itself, A is equal to SD itself, was making sure that we are dealing with linear problems. So that S was linear. Okay. Now, what happens if S becomes nonlinear? So for example, if our S stiffness matrix, I'll be using K and S interchangeably, please. If you are confused, just stop me so I'll clarify. A is equal to SD, and if suddenly S becomes nonlinear, what does that mean? That it means that for different values of D, my S does not remain constant. So as I change my value of D, so if D is equal to 1, any unit you can assume. So if D is equal to 1, my S is certain value, but as I increase my D value to 2, my S changes its value. Then can I say that A1 plus A2 is equal to S D1 plus D2? No, because my S was changing its value in the way. Agreed?
Yes, sir.
Yes, sir.
Right? So that's when the problem becomes nonlinear. And nonlinearity can come, as I was saying, from material nonlinearity or geometric nonlinearity. Material nonlinearity typically is because of the yielding of the material or fracture of the material. So fracture can come from various sources, which I don't want to get into, and solving a problem with fracture is a completely different ballgame. That's not within the scope of this course. Yielding is a more gradual kind of a nonlinearity, or concrete does not yield, but still concrete has a pretty smooth, or at least confined concrete does have a very gradual nonlinearity, which to some extent can be incorporated by these methods that we are going to discuss. Okay, so that is material nonlinearity. Even if, let's say, you're talking about yielding of steel, so steel has a bilinear behavior, right? Mild steel, at least, that has a bilinear behavior. What do I mean by bilinear behavior? What is meant by bilinear behavior?
Before yield point, the stress strain curve will be 1, and after yield, it will be another 1.
Sorry, can you repeat the second part?
Like two stress strain relationship can be given in two relationships.
Correct. Very good. Yeah. So basically, there are two different values of stiffness, right? So one stiffness value, and suddenly at one point the stiffness value changes to a new value. Correct. So that can be given as two equations, two linear equations. Alternatively, some material like concrete, for example, cannot be fit into a bilinear behavior. So it is more like a curvilinear behavior. So up to some point, it remains linear. After that, it follows a curve, and there are equations, empirical equations available in the literature, which you can use to idealize that stress strain curve for concrete also. Fine. So even for those materials, if you see, the material behavior may sometimes be bilinear, which is a sudden change in stiffness, but the structural behavior or the member behavior is often curvilinear. It's not bilinear. It's hardly ever bilinear. And there are various factors. There are residual stresses. Sometimes you may have bending behaviors, and under bending, your fibers reach the yield point gradually. And because of all those things, we have done the steel design course, right? So steel design course we just finished, right? So some parts we discussed this thing in that when you apply a residual stress effect we had discussed, you remember? Most of you had taken that course. So a column under compression, even though the fiber behaves, individual fibers, individual coupon behaves bilinear, the column itself does not behave bilinearly. It behaves in a curvilinear manner. So typically for most of the members, under most of the conditions, you have a more gradual change in the stiffness. Okay, even if the material may be changing more in a more sudden manner. Fine. So one method is one type of nonlinearity is coming from material. Another type of nonlinearity comes from geometric nonlinearity. Okay. So geometric nonlinearity again is a very broad word. There can be very many number of types of geometric nonlinearities that can come into the play. Can somebody give me some examples of what types of geometric nonlinearity you might have come across?
Initial crookedness, sir.
Harish, louder and repeat again, please.
Initial crookedness, sir.
Initial imperfection, initial crookedness. Yeah, so initial crookedness, actually, I understand what you are saying. It's basically also known as P delta effect. Okay, so if a column is not perfectly straight and you apply axial load to the column, okay, so that axial load acting on the column will introduce a moment because the member was not perfectly straight. Okay, so even if the axial load is concentric, it is acting right at the centroid, still it will produce a moment. So, and there are varieties of these P delta effects. One is because of the initial imperfection. The other one could be because of the eccentricity of the load itself. Okay, and so on. So that is called P delta effect. Okay, that is the generic term that is used for that kind of a nonlinearity. Very good. So that is P delta effect. Then there are actually two types of P delta effect. One is known as P small delta effect. The other one is known as P capital delta effect. This triangular delta effect. If we take a course, if you happen to take a course on stability, we will be talking about these things in more detail. One is more applicable to non-sway systems. The other one is more applicable to sway systems. But I will not have time to discuss that in much detail here. So that is one type of nonlinearity. Any other type of nonlinearity you may have? Geometric nonlinearity I'm talking about. What other type of geometric nonlinearity can there be?
Change in boundary conditions, differences in the boundary conditions.
Explain, please.
If a boundary, if you are fixing it as a fixed beam, it may not be actually completely fixed. So there can be some kind of rotations in it.
But that's not necessarily non-linearity, right? I mean, if there is a rotation that could be modeled using a spring, and if that spring is linear, then the problem remains linear. And if that spring is non-linear, where like you're saying, it's partial fixity, right? That's what you mean.
Yes, sir.
So
yes.
Partial fixity can be modeled with a spring. Now, whether that spring behaves linearly or non-linearly, that depends on how strong that rigid thing is. And if it is non-linear, then it is more into the material non-linearity side, because it's probably that material that is not behaving linearly. Okay, I would not call it geometric non-linearity. Okay, and there is no reason to assume that partial fixity will always be non-linear. It can also be linear. partial fixity can be linear too. So then it does not necessarily lead to nonlinearity. And even if it does, it is more of a material type. Any other example of geometric nonlinearity?
Sudden change in geometry.
Sudden change in geometry. Elaborate, please.
So the cross-sectional change, sir.
So like, as you're saying, the member length, along the length of the member, the cross-section changes its size. No, that is a linear problem. You can solve that problem with whatever we have discussed so far, with a few assumptions along the way. You don't have to worry about geometric nonlinearity or any kind of nonlinearity there. One thing I can point you to, you may remember the relationship between curvature and y double prime. Let me start. So if you remember, when we were deriving this is the x-axis, and there is a beam. That beam could deflect this way. Okay. This was the curve of the beam. We had derived the expression for curvature. So if I take a small portion of this curve, okay. So we had defined the phi value. We had not derived this expression, but you must have done this in your undergraduate level. There is a curvature phi, which is basically 1 is divided by r. This is that radius. Okay. Assuming that this is a small segment of the beam, okay, which I can define at every few. So I'll call it ds. S is the like secant sort of a thing. So as you are moving along the length of the member, you are traveling s. Okay, so at location s, you have a small segment of ds length, which has a radius of curvature r. So its curvature will be 1 by r, 1 divided by r. Okay, and that we had calculated to be equal to y double prime. Okay, and this assumption was true, or this expression was true, or approximate. It was okay to approximate this as long as y prime was small. If y prime was not small, then phi was a function of y double prime divided by square root of 1 plus y prime something. I think 3 by 2 or something. Anybody remembers what is that expression? You don't remember?
Yes, sir, 3 by 2 less.
Probably this one. Don't quote me on this one. So I don't remember exactly, but it was something like this. So as soon as you get there, then the problem becomes nonlinear. So that is also one type of geometric nonlinearity, which arises when you have large deformations. Okay. Also, you have a geometric nonlinearity because of the difference between. So there are different types of geometric nonlinearities, or various sources of geometric nonlinearities. One is your P delta effect. So P delta effect, again, it could be because of geometric imperfections. Geometric imperfections. It could be because of P and M acting together. Okay. Then the other one is your large y prime value. Okay, so if it has a large deformation, then your y prime will be, or slope of this line will be large. Then your phi is not equal to y double prime. It is actually equal to this expression that will introduce nonlinearity in the problem. Right? So because we were relating phi with m, right? So phi was equal to m was equal to something phi. What is it? M M was equal to how much times phi?
EI fee.
EI phi. Correct. So as soon as and that's where we were putting y double prime. If that is not y double prime, the problem will become nonlinear. Okay. Then you may also have nonlinearity because of the differences between engineering stress strain versus true stress strain. You remember the difference between them? So even if the material is assumed to be behaving linearly, yeah, somebody wanted to say something? Okay. So even if, engineering stress strain is generally assumed to be linear. So even if the engineering stress strain is linear, the true stress strain values may not be, the curve of true stress strain may not be linear. And there will be Poisson's effect, and that will change the cross section. So as a result, at a large strain rate, at a large strain value, even if we are not going into yielding, the material is such that it doesn't yield, or for whatever reason. So still, because of the large strains, your Poisson's effect will be so severe that cross-section area will change, and that will have an effect on the overall linearity of the problem. Okay. So even this is even if you assume the engineering stress strain to be linear, under large deformations, the behavior will be different because true stress strain will not be linear in that case. Okay. And there can be a few more I am not able to recall off the top of my head right now. But as civil engineers, we have to deal with this kind of a nonlinearity more often, geometric imperfections and PM acting together. So these are the two. I'll give some detailed examples here. So geometric imperfection could be if I have a column, or I was supposed to have a column placed like this, right? And an axial load was acting. This column is perfectly straight. No matter how much load I apply, there is no reason for this column to have any lateral movement, right? The column is perfectly straight. If the column is perfectly straight, it would not deform laterally, right? But if the column was not perfectly straight, it was slightly crooked, it was already having some crookedness, some imperfection, geometric imperfection, which may be, if the length is L, this imperfection could be, say, L by 1000 or L by 5000 or 10,000, anything, even a small deformation, even a small imperfection. And then I apply a load P. Then what happens is that this load P is supposed to be resisted by load P here, or the reaction here, with perfect alignment. But if I draw the free body diagram of half of the column, and I'm exaggerating amplifying the imperfection here. So this is whatever L by 1000, let's say. This P has to be applied here, right? This is how the P must be coming in. And this is, I've drawn the free body diagram of this part. Yeah. So the two P values are not aligned. The two P forces are not aligned. And as a result, there is a moment, and that moment has to be resisted by an internal moment acting this way, right? So the two P's, they are making the column rotate in the anti-clockwise direction. So the internal moment has to be applied in such a way so that it is balancing it. And that moment will be how much for equilibrium?
EI5.
For equilibrium, just look at the equilibrium equation.
P into 12.
PL by
Yeah, PL by 1000. Okay, and it will be different at different location. At this location, it will be PL by whatever this is, right? Whatever this delta is. So PL by 1000 is maximum delta. L by 1000 is here, but here it is not L by 1000, it is less. So that's how the M will be different. Okay. So this L by 1000 here is known as small delta because it is for a non-sway case. So that at the top and bottom, you don't have any deflections. You have only deflections in the middle because of the imperfections, and that you will know as small delta. This is called P delta effect. You can see it, P delta effect. Fine. Similar thing can happen for a cantilever column. A cantilever column, which was supposed to be a perfectly straight column, for some reason is not perfectly straight. It has a small deflection, we'll call it delta. Okay, small imperfection to start with. And because of that, there will be a moment acting here. So if I apply a P load here on the imperfect column, that imperfection will introduce a moment demand here. It has to be resisted, that moment. So that will be equal to P times delta. Agreed? So it is known as P delta effect, P delta effect. This one is more applicable for sway cases. This is more applicable for non-sway cases. Okay. You may also have a situation where you have a beam. I can give you a column of an example of a column also, but a beam is more apt here. And the beam is carrying some axial load, so it's more of a beam column. And then for whatever reason, you have moments acting on the beam. This is a roller support, this is a pin support. And I have two moments acting. If these two moments were acting by themselves, there was no issue. I could solve this problem easily. But along with these moments, if I have an axial force also acting, okay. So as soon as I bring these two in, what happens is that because of these moments, the beam will deflect how? It will go into hogging or sagging?
Hogging, sir.
Hogging, right? So the beam will be deflecting this way. And then imagine that because of these M's, the beam has deflected. And at that time, only M were acting, the beam had deflected. I could solve this problem. But now I have applied P in addition to that. Okay. And this P will introduce an additional moment, just like it was doing here. It will introduce an additional moment. Okay. And that moment will depend on how much was the original deflection. This deflection was a function of M in the first iteration. But if you go subsequently, then the additional deflection will come in, secondary, it is known as secondary deflection. Okay, that will be a function of delta that was primary. So I'll write it as a function of delta primary and also P. Correct? Makes sense? Because as the P increases, your moment demand changes, and that will introduce the additional deflection or additional. So this deflection keeps getting amplified because of an increasing value of P. Okay. So this is also one type of nonlinearity, geometric nonlinearity, which is P and because of P and M acting together. If instead of P, it was T acting on the column, that is tension force. So these two moments would make the column or beam bend this way. But if I apply a T also on top of this, okay, then what will happen? Because of this T will be resisted from here, right? And as a result, your net deflection will be lower. Originally it was this much, but now it will be, because of the presence of T, your deflection will be lower. So T will have a more stabilizing effect, whereas P will have a destabilizing effect. Fine? Makes sense, right? So yeah, so this is also one type of geometric nonlinearity. So we will discuss Newton-Raphson method in today's class and maybe some part of tomorrow's next class, and discuss how to solve such kind of problems which are arising, where the nonlinearities are arising out of either material nonlinearity or geometric nonlinearity. The problem is since it's an iterative method, it is numerically intense, and it is very difficult to solve a real life problem in a classroom, right? So unless you use a computer, it becomes very difficult to solve any decent size problem in a classroom. So what we will be solving in the class are kind of springs or very simple trusses. Okay. As soon as we get into a real size problem, the problem explodes in size, and then we have to deal with large size matrices and number of iterations we have to do. So it becomes a bit complex. Anyway, you already have the lecture notes, which are lecture notes 4, right? And this is basically one numerical method of solving nonlinear systems. This method works very well for all the problems which are becoming softer. Okay, it has some difficulty sometimes in handling problems which are becoming stiffer, but it can sometimes solve. But for problems that are becoming softer, it is very powerful. It can handle the issues very well, as long as the stiffness of the problem does not become 0. Okay, so when I say stiffness does not become 0, what I mean is that if you draw the force displacement curve, the problem starts with this kind of stiffness and it goes on to like this. So up to the point where it becomes 0. So at this point, the stiffness has become 0, the slope has become 0. So up to this point almost, it can solve. Newton-Raphson is very effective and it can get you a solution up to that point. Yeah. Okay. So here in this plot, maybe in this figure, if you look at the two axes, the horizontal axis is representing the deformations, the vertical axis is representing the force. And this is drawn keeping a single degree of freedom kind of a system in mind. But for a multi-degree of freedom system, it's very difficult to say which deformation we are talking about, because deformation is not a single deformation. It's a number of separate degrees of freedom. So then it is more of a schematic. It is more of a idea thing rather than like literally looking into it. But anyway, this is very powerful diagram for you to understand the process. Okay. So the way Newton-Raphson method works is like it works in solving any polynomial problem or any algebraic equations, any number of algebraic equations. The way it works is that first you need to know at least one solution to start with. Okay. So for any structure, for example, what solution do we always know? So a structure is given to you, and I want to know what is the deflection of this structure when I apply this load. So I don't know what is the deflection when the load is this much. Let's say load is 100 kilonewton, and I don't know what the deflections are at that 100 kilonewton. But there is, at least for one load, I know the deflections. What is that load value?
Dead loads.
Sorry? Dead load?
Yes, sir.
No, but for that you have to solve the problem, right? For the dead load. But even before solving the problem, I know the deflections for one load value. It's a trick question. There is no
0, sir.
zero. Yes. Yeah. So like we are always assuming that the system, when you have not applied any external forces, the system has 0 deflections. Correct? Or there are no internal forces in the system. Okay. Those things we are assuming. So, and that is mostly true. That's how we build the structure. If there was an internal force, we would not have been able to assemble the structure at the first place. Fine. So at that time, the deflections are 0 when the loads are 0. That will be the starting point. So that is basically on this curve, if you see, at least that is one starting point where we know the solution exists and it lies on that curve. Okay, that is 0, 0. 0 deflection, 0 force. And then let's say the problem is given to me that, okay, this is the structure. You have to solve this structure for a 100 kilonewton load acting at a particular location. Fine. If the problem were a linear problem, what would I do? Imagine it's just a spring, single degree of freedom. One point is fixed, the other point is free to move. It's a spring. And I'm asked, if I apply a 100 kilonewton load here, what will be the deflection? What do I need to know to calculate the deflection?
Only
Stiffness of the spring, sir.
Stiffness of the spring, correct? So if it's a linear spring, I just need to know one stiffness value, that is K value. Okay. And what do? I take that force, divide that force value with the stiffness value and get a deflection. That is the deflection of the spring, right? That is exactly what we do even for a nonlinear problem in the first step. So let's say I have this problem. I know that this is how it's going to behave. I don't know the exact behavior, but I know that this is a nonlinear problem. So the curve looks somewhat like this. I don't know the exact curve. But what I know is that there is an equilibrium point here. When I did not apply any force on the spring did not have any deflection. That is my equilibrium point, right? That's the definition of equilibrium. So you have zero deflection and zero force. That is my first equilibrium point. Then I know what is the stiffness of the spring at that point. When there is zero deflection, what is the stiffness? I may not know the stiffness right now, later on. So when I apply 100 kilonewton, what will be the stiffness? I may not know, but I know the stiffness now. When the force is zero, the stiffness is this much. That stiffness is given by the slope of the tangent drawn on this curve. And I am told that 100 kilonewton load is applied. So what do? I take that 100 kilonewton, divide with the slope, and I'll get the deflection. This will be my deflection calculation for a linear spring. If it were a linear spring, the system that is behaving like this, if this were not a nonlinear system, it were a linear system, it would have followed this curve and would have given me this much of displacement, UA. Okay, that is just like any linear system. But now comes the trick. What will happen is that in the process, as you apply that force P, you will assume that you have applied full force P and you will get certain deflection. Then you look at that deflection, and for that deflection, you work back what is the force in the spring. And what you will see is that actually spring has not developed this much of force, but it has developed only this much of force, because along the way, it bent downwards. This curve did not continue on this path, but it bent downwards. That means it did not develop all that force. It developed smaller force. And as a result, there will be an unbalance. So let's say the spring did not carry 100 kilonewton. The spring, let's say the stiffness was 100. The spring stiffness was 100. You apply a load 100. So the deflection you were expecting was 1. Okay. So you did that. You check. Now after one deflection, you look at that one deflection value and looked at the spring behavior. Then when you looked at the spring behavior, you found that no. Okay. When the deflection was 0, the spring had a stiffness of 100. But when by the time the deflection became 1, the spring did not develop 100 force. It actually developed only 50 force. Okay. So the curve was bending downward. You are following me, right? You guys are with me. So instead of developing an internal force of 100, the spring developed only 50. That means there is an unbalanced force. I had applied 100, but the spring is resisting only 50. That means another 50 has to be applied on the spring. The spring has to resist an additional 50. That will become my unbalanced force. And at this time, what is my new stiffness? You will see that, okay, my new stiffness is maybe not 100 like it was before, but my new stiffness is only 33. Okay. So the remaining 50 divided by 33, so this is the remaining 50 divided by this slope 33 will be giving me additional deflection. Okay. So that will be deflection between A prime and A. That is my additional deflection. Fine. And by that time, we will see that no, actually it has not been able to even resist the remaining 50 kilonewton now, because the stiffness was further declining. So it did not follow this path, but it was following this path, right? So there will, after every iteration, you will see that there is some unbalanced force, and that has to be balanced again. That means there will be additional deflection. So what could have been a UA deflection, after a number of iterations, it will turn out to be a U1 deflection. Okay, and that's how you get the next point of convergence. When you see that the unbalanced forces, the force values are very, very small now, then you can say that you have reached the convergence and the system is in equilibrium. You are following me, right? So in that process, if you're following this process, there are 2 or 3 things that you need to do in addition to the stiffness method that you have learned. One thing is that you need to know the stiffness, and you need to know not only the original stiffness, but stiffness at every step of the way. So original stiffness you needed, but also you need the stiffness after first iteration, after second iteration, and the stiffness value keeps changing. Agreed? So that is called calculation of tangential stiffness. Is that okay? So that is additional work in addition to whatever you have learned in the stiffness method. Another thing that you have to do is, after calculating the stiffness, you divide the force with the stiffness. That is same as your stiffness method, because you are already doing that. When you were saying A is equal to S multiplied by D, force was equal to stiffness multiplied by displacement, you were, in order to solve for the displacement, you were dividing A by S. A divided by S was displacement that you were doing before. You also need to do that. So that is same step as before. But now, after you calculate the displacements, you have to calculate internal forces. Okay, and you have to check for the balance of the forces. So calculation of internal forces is called state determination. Once you know the internal, all the displacements, you look at the constitutive behavior of each member and calculate the internal forces and add all those internal forces to check with and or to balance it with the external forces that were applied. And if there is any imbalance, that will be the unbalanced force for the next iteration. Okay, and that's how you proceed. So there are three significant steps, in my opinion. The middle one, that is pretty much exactly the same as it was before. That is calculation of deflection for the unbalanced forces based on the tangential stiffness. But the first step, that was calculation of tangential stiffness. Earlier, it was just simply calculation of stiffness. Now it is calculation of tangential stiffness, and that you have to do in each iteration. So this will be the first iteration, this will be the second iteration, this will be the third iteration, and so on until you reach the point of convergence. And the third step, that is called state determination, which is nothing but calculation of internal forces for the given displacement values, or the displacement values that you have solved in the second step. Yeah. Okay, so I hope you were listening. None of you were asking or stopping me. So can somebody tell me what are the three steps in the Newton-Raphson method? In a single iteration of the Newton-Raphson method, there are three steps involved. Which are those three steps and how are they used to solve it? Monish, you want to give it a try?
Yes, sir.
Yeah.
First, for a given load, we calculate that displacement. So, what is the variation we know? Like that force it didn't take.
Yeah.
Variation.
Unbalanced force, you mean?
Yeah, yes, sir.
Yeah. And
so we know that. So based on that, we draw another. So like the iteration continues like that.
I was hoping you would give more details or more keywords here. In general, it's okay. Yeah, you calculate unbalanced forces. Unbalanced force calculation is an important step. We call it state determination. That was the third step out of the three steps. The first step was Haripriya.
Yes, sir. Sir, initially we do what we did as before. To calculate the deflection, we divide the force with the corresponding deflection. After that,
Force with the stiffness. You divide force with the stiffness,
okay,
not deflection.
Okay.
Yeah.
And then in the upcoming step, we have an unbalanced forces. For that, we repeat that iteration um, to converge the value.
In general, it's okay, but I was hoping a more precise answer. Yeah, both of you can mute yourself. Mohan Krishna.
First, we will find for a given load what is the deflection.
How do we know the deflection?
The stiffness by force.
So how do you know the stiffness?
So
at what stiffness? See, stiffness. I mentioned this is nonlinear problem, right? So stiffness is changing.
Yes.
We call it tangential stiffness, tangent stiffness, right? And that stiffness belongs to the known point of convergence. So we start with, so let's say there was a point of convergence. For any system, it is usually 0, 0, 0 force, 0 displacement. So at that point, we calculate the tangential stiffness. Okay. So at that 0 point, what is the stiffness? When there is no deflection. That stiffness we start with, and subsequently with each iteration, we will revise that stiffness value. Okay. So that is called first calculation of tangential stiffness. That is the first step. Okay, go ahead. So what do you do with that tangential stiffness?
And from there we, due to the unbalanced forces, then we will have there is a change in stiffness.
Not quite yet. Okay, so basically what do you do with the tangential stiffness first? You got the tangential stiffness value, you got the force demand.
And we'll find the deflection.
We find the deflection. How?
Tangential stiffness by force.
Force by tangential stiffness. Force divided by tangential stiffness.
Yeah.
Fine. So you got the displacement. That is your first iteration displacement or zeroth iteration. Some textbooks call it zeroth iteration. Some textbooks call it first iteration. Fine. You got your deflection. Then what do you do from that deflection? Okay, Ranjit Kumar.
Yes, sir.
Yeah. So you got the deflection values. What do you do the next? See, you guys, if you are not listening in the class, and then it will not be very good. I'm making a note of who are listening, who are responding, who are participating. This matters, right? Asadullah?
Yes.
Yeah.
After getting the deflections, we calculate the force, sir.
Which forces?
Actually, internal forces.
Internal forces. So the deflections, from the deflections, basically there will be some step inside. Once you get the deflection at the degrees of freedom, from there you have to calculate the deflections or deformations of each member. Correct? And then for each member, once you know the deformations, you can calculate the internal forces. Right? Okay, go ahead. Then what do you do?
Then again, we have to check the actual force minus internal forces, unbalanced force.
Yeah, so you have to check for the equilibrium. So the word for that is equilibrium. So the internal forces should be balancing the external forces. Good. And then maybe I'll ask somebody else. Amulya, what do you do then? You check for the internal, you check whether the internal forces are matching the external forces or balancing the external forces.
Then we have to start another iteration, sir.
What will be like, what do you mean by iteration? What is the next step? Iteration is the way.
Find the tangential stiffness again, sir, like the slope of the curve.
Okay, and
then again we have to calculate the deflections.
How do you calculate the deflection?
Force by stiffness.
Which force? Which force?
Unbalanced force, sir.
From the previous iteration.
Yes, sir.
Okay. Yeah. So that is the new deflection that you add to the previous deflection. That is your total deflection after first and second iteration. Right. And then again, in the second iteration, again, because you got the new deflections, you will see that with the total deflection, again, you do the state determination. What is the meaning of state determination, Sairaj?
Sir, that is the point where the internal force is equal to the, like, what convergence has occurred, sir.
No. That is convergence point. State determination. What is the meaning of state determination? I had mentioned that. State determination. Okay, so state determination is basically, once you know the deflections, from that, deflections are basically at the degrees of freedom. So from those deflections, you need to know the deformations of each member. Correct? So for example, let's say these are two spring system, okay, or two members. So I have deflection here. This is fixed, let's say. I have D1, first degree of freedom, second degree of freedom. I have D1 is equal to 5 and D2 is equal to 7. So what are my spring deformations? This is first spring, this is second spring. So what is spring deformation? Sairaj?
Yes, sir.
What are the spring deformations?
Sir,
this point is moving by 5 millimeter, this point is moving by 7 millimeter. What are the spring deformations? Can you see my screen?
Yes, sir. Yes, sir. Yes, sir.
Yeah.
Sir, even the spring will be moving by 5 and the second spring will be moving by 7. Sir.
Second spring is deforming by 7?
So, 2, sir. 2, sir, I guess.
2. Yes.
Yes, sir.
So that's what. So the state determination first requires before the state determination, when you solve the system, basically you would know the force value, unbalanced force value. I'm just writing it F, which is unbalanced force, is equal to S times D, or A multiplied A is equal to S times D. So from here you will get the D values. These are nothing but D's. Okay, D1 and D2. So you have 2 degrees of freedom, so D1 and D2. From here you have to calculate internal deformations. From internal deformations, you have to calculate internal forces. So both springs will have some constitutive relationship, which will give you the internal forces. Okay, which will depend on how much deformations each one of them have. And from these internal deformations, you have to do the equilibrium. So sorry, up to here, this step is called state determination. Sorry, my bad. From here to here, this is called state determination. You guys are following me?
Yes, sir.
Fine. This was solving of the system. Before that was the tangent stiffness. Okay. So the first step was tangent stiffness. The second step is solving it to calculate the deflections. Third step is state determination to calculate the internal. And the fourth step is from the internal forces you calculate the unbalanced forces.
Sir, so for every step we find the state determination, sir?
Yeah, for each iteration.
Okay.
So within one iteration, you have to repeat these 4 steps.
Okay.
Calculate unbalanced force. Then the next iteration again, for this deflection, the values that you had got here, for this deflection, again you repeat the process. You calculate the new tangent stiffness.
Okay, sir. Sure.
Okay. Then the second step where you calculate the new D values, D new.
Yes, sir.
You calculate the same thing, step 3, step 4.
Okay, sir.
Okay.
Yes. Thank you, sir.
All right, so let's do some examples here instead of keep talking about abstract things. So through examples, it will be much easier to solve. I want to do at least 2 examples today, and then one example on geometric nonlinearity will be pending that we will do in the next class. So this is a 2-spring system, just like the example I was showing you just now. These are 2 springs attached in series, right? And a load 5 kilonewton is applied. One of the springs is straight spring, so it's a linear spring. Spring 1 is linear, not straight. I'm sorry. It's a linear spring. So K1 is equal to given as 1. Spring 1 is having a stiffness of 1. Fine. Spring 2 has a nonlinearity. So it is not a gradual nonlinearity, it's a sudden nonlinearity. So up to this point, it is having a stiffness of 2. And beyond that, it has a stiffness of 2/3. Fine. So it softens at this point. The deflection at that point is 1. You follow me? So these are the 2 systems. Now, since this is a very, very simple system, we can solve it very easily without even having to use any Newton-Raphson method. So that will be a check for us, right? But this method will not work for a more complex system. So you have 5 kilonewton load acting. Since the 2 springs are in series, what will be the force in each spring at the time of equilibrium? 5 kilonewton, right? Right. So each spring is carrying 5 kilonewton. All I have to do is look for spring 1, because they are in series, they have to both carry the same force. If they were in parallel, both of them would be having the same deformation. So I just have to go to 5 kilonewton line, and the deflection for the blue one, that is spring 1, will be 5, right? Because its stiffness was 5. Its stiffness was 1, sorry. It has K of 1. So straightforward, I get a deflection of 5. Okay, at equilibrium. For the second one, it is not really 5, it is somewhere here, right? And if you substitute the value of force 5, you can see that this deflection turns out to be 5.5. Okay, that is pretty straightforward, right? Because I know the spring behavior already. So for a force of 5, crosses the horizontal line of 5 is curve. So that is a deflection of 5.5. No magic here, no tricks here. So I got a deflection, spring deformation of 5 here, spring deformation of 5.5 here. What are my deflections? Let's say it's my D1, this is my D2. What are my D1 and D2 values? What is the D2 value?
0.5, sir.
0.5?
10.5.
10.5.
10.5.
Yeah, 5.5 plus 5, 10.5. So these are the two deformations I get. Two deflections I get, sorry. These are the deformations. These are deformations. These are the two deflections. Got it? So the final solution is going to be 5, 10.5. So that is kind of a check for me to see later. What is the deflection here? What is the deflection there? Of course, 0. That's the one solution. So I have to report only two deflections, one here, which is 5 and 10.5. Now let's use the Newton-Raphson method. So Newton-Raphson method, first we calculate the stiffness matrix, right? So spring is nothing but, I can take the degrees of freedom 1, 2, and 3. So for the first member, there are 2 degrees of freedom. So it's just like a truss member. What is the stiffness of a truss member? Correct? Because in the truss, we had this degree of freedom also. So therefore, you had 1, 0, 0, etc. 1, 0, minus 1, 0, and so on. Right? But since we don't have that, this is single degree of freedom in single axis. So we have only 1, minus 1, minus 1, 1. It is okay? Anybody has a problem about how we got this stiffness matrix?
No, sir.
No, right? Because we don't have the movement in this direction. A truss member would have it, but since it is only in, everything is only in one axis, we have only one direction. So that's why those 0 terms will go away. So we got 1, minus 1, minus 1. Basically, what it means is that if I apply a unit deflection here, I'll have to apply a unit force here, AE by L force here. So instead of AE by L, this time the stiffness is given as 1. K1 is equal to 1. So this is the stiffness matrix for member 1. For member 2, what is the stiffness matrix? In the beginning, what is the stiffness matrix? K2 is 2, right? So 2 multiplied by 1, minus 1, minus 1, 1. Later on, when it is in this part, what is the stiffness matrix?
2/3 of 1.
2/3, 1, minus 1, minus 1, 1. Everybody agrees with this? This is called spring 1, stiffness matrix. This is spring 2. Okay? So, member 1 or spring 1, stiffness matrix. Member 2, spring stiffness matrix in the beginning. So, right now we are at this state. We know that both springs have 0 force and 0 deflection. Right? But now we have got an unbalanced force of 5 kilonewton. So, what is the unbalanced force? We'll see in a minute. So, first we will assemble the stiffness matrix because we are following the stiffness method. So, we are merging the stiffness method with Newton-Raphson method. So, how do we do that? This is spring 1, this is spring 2. I'll erase all this part. Which degrees of freedom does the spring 1 belong to? 1, 2, 1, 2. Correct? Which degrees of freedom does spring 2 belong to?
2, 3. Same, sir. 1, 2, 1.
No, not 1, 2, 1, 2.
2, 3, sir.
2, 3, 2, 3.
Right. So basically the total stiffness matrix will be, if I may write it here, 1, minus 1, minus 1, 1. And plus there will be a superimposition of this part, which will be plus 2, minus 2, minus 2, plus 2. And zeros here. Okay. So basically, this is the total stiffness matrix. Out of this, we have to take SFF. Remember? SFF is which part? Second and third. Second and third. These are the 3 degrees of freedom. SFF will be equal to 3 minus 2 minus 2. So this is my SFF stiffness matrix. Okay. The force, right now you ignore this part. We will see that in the next iteration. So the force vector is 0, 5, 0, 5. That is free force, or force in the free degrees of freedom. So which degrees of freedom are free? 1 is free.
No, sir.
2 is free.
Yes, sir.
What is the force acting at 2?
5 kilometers.
At 2 degrees of freedom, what is the force acting here? External force.
0, 6.
External.
What is the external force? Yeah, what is the external force here?
5,
5, sir.
5. So we got external force of 0, 5 at second and third degree of freedom. First degree of freedom we don't report because we are writing the equation AF is equal to SFF DF. Right? So AF is equal to second and third degree of freedom, which is 0, 5 is equal to SFF DF. So this is my SFF, and we take the inverse of that one. If you take the inverse of this matrix, you get a matrix like this, multiplied by your force vector, that is 0, 5, and you get a deflection of 5, 7.5. What did I get the deflections as? I got the deflection of 5 here and 7.5 here. Right? What is the next step? So I have just completed two steps. Calculated the stiffness matrix, that is tangent stiffness matrix, and I have solved the system to calculate the deflections. Now, what is the third step? What was the third step?
State determination.
Yeah, and what is the part? What are the two steps within that? Within state determination?
We have to find the deformations and internal
Deformations. So these are the deflections. Very good. So now we have to find the deformations. The deformations will be in this spring. How much will be the deformation? And in this spring, what is the deformation?
2.5.
2.5.
2.5. Very good. So the internal forces will be
5.
here. Something here, right? So we have to do this calculation, which turns out to be 3. The force in the first spring is 5. In the second spring, it is 3 actually. So it. Sorry, did I make a mistake here? So for 1.5 multiplied by 2 by 3. 1.5 multiplied by 2 by 3 is how much?
One, sir.
Oh, sorry, I'm calculating. What am I doing? My bad. Sorry. Yeah. So instead of say deflection, I know, right? So deflection is 2.5. So deflection is 2.5 here. For that 2.5, I'll get a force of 3. Okay. So these are the internal forces. F internal. Agreed? So the first spring has an internal force of 5. The second spring has an internal force of 3. There is obviously an imbalance. What is the imbalance? If I can draw the first spring, it has an internal force of 5. That means it is, let me draw the forces at the joints. The fixed end, the middle point, the last end. This end is being pulled by 5 kilonewton by the first spring, and this point is also being pulled by 5 kilonewton. The second spring is pulling this point by what force? Internal force of the spring? 3 kilonewton.
3.
The third point is being pulled by the spring by 3 kilonewton. And externally, I'm applying 5 kilonewton. Now, what are the imbalance? See, here there is no imbalance because this is restrained. I don't worry about the restraint point. Only the free degrees of freedom. This will anyway absorb all kinds of demand. This one is not a problem. This one, what is the imbalance? What is the imbalance here?
2.
Correct? These are the unbalanced forces. So the first, so this is the out of balance or force. So out of balance force is -2 in this degree of freedom and 2 in this degree of freedom. -2 and 2. Got it? So now we have completed the 4 steps. We have calculated the unbalanced force. Now going back to iteration 2. So this is your iteration 2. For iteration 2, again, we will calculate the stiffness matrix of the first member, stiffness matrix of the second member. Now you may notice that the stiffness for the second member, earlier it was 2 here, now it is 2/3, because you may recall our deflection in the second spring had become 2.5, and at 2.5 deflection, you are already in the second zone. Correct? After 1 itself, you are in the second zone. So you're already in the second zone. So now you have to use the new value of stiffness, which is 2/3. Okay. So this is the SFF matrix. By assembling these two, I assemble these two, I get SFF. I take the inverse of that and pre-multiply with the unbalanced force. What was the unbalanced force? -2, 2. Right. So I pre-multiply the inverse of the stiffness matrix with the unbalanced force matrix. I get the new deflection matrix 0, 3. So the total deflection will not be 0, 3. The total deflection will be whatever I got in the first iteration plus the new deflection. So the first iteration deflection was 5, 7.5. So this will be 5, 7.5 plus 0, 3. So that is basically 5, 10.3. Sorry, 10.5. Right? So this is the second iteration, total deflection. I can calculate the internal deflection, internal deformations in each spring. So for 5 deflection, deformation is 5. For 10.5 deflection, the deformation is 5.5. Obviously, right? And then the forces can be calculated. The forces are calculated 5, 5. You will see that now it is balancing the forces perfectly well. Okay, so there is no error, and the final deflection is what you had calculated here, 5, 10.5. Is that matching with what we had estimated before?
Yes, sir.
Yeah,
Yes, sir.
this is what we had estimated before. So this was a very, very simple problem. Of course, Newton-Raphson method did not make much sense here. Why would you use Newton-Raphson method when you could solve it very simply like this? But still, it was an easy way to show how effective it is. And for subsequent problems, which are much more complex, you will see the effectiveness of this method. Okay, and it can be used for a much more complex problems as well. All right. I don't know whether we have time to complete the second problem. Do you guys have a class immediately after this? After 12:30, do you have a class?
No, sir.
No, sir.
Okay, so then maybe I'll extend it by another 3-4 minutes just to complete this second example. Second example is also on springs, because I don't want to deal with a problem which has 10-15 degrees of freedom, and any realistic problem will very easily get there. Because then you have to do 3-4 iterations also to reach a decent solution. But anyway, so that's why I'm solving in the classroom only the problems with the springs. But you can use this method exactly. But since the formulation is exactly like what you would have for a stiffness method, you can very easily adopt this method for a problem which has frames and trusses, etc. Okay, moving forward. Now you have another system of springs, but in this case, load is here. The 3 springs that are given to you, 2 of them are in series and they are in parallel with the third spring. Okay. So can you please identify how many total degrees of freedom are there? This is a single boundary. Both this end is tied together, and this is another boundary. What are the total degrees of freedom? Salman? Salman? Can you hear me? Tekeshwar? What are the total degrees of freedom here?
3, sir.
3. Very good. Yeah. 1, 2, and 3. Out of these 3, which are free and which are restrained?
2 and 3, sir.
3 is free and 2 is free too. Correct. So 2 and 3 are free and 1 is restrained. Correct. So it's size wise, it's the same size problem, but this time we have got 3 springs here. Okay. Now the 2 springs F1 and F3, or first and third springs, they are all linear. So this is your third spring F3. This is your first spring F1. The second spring is nonlinear, which is the expression is given by this one. So your F for the second spring is equal to 2 square root of D2 is basically deformation of the second spring. So D plus 1 minus 2. If I want to calculate the stiffness of this one as a function of D, what will be the stiffness? That will be a derivative of D. What will be that? Are you okay? Is that okay? Isn't it? It will be basically 2 divided by square root of
Yes,
d
sir.
by d plus 1 and another half. Yeah. The 2 and 2 will cancel out. You are left with 1 divided by square root of d plus 1. Okay. Or d2 plus 1, whatever. So this is the stiffness of this matrix. So the stiffness of this one is 1. Stiffness of this one is 2. And the stiffness of this matrix is, this spring is 1 divided by square root of d plus 1. Fine. We have to solve this system for the given force 10 kilonewton here. Now, can you solve this system like we had solved it before without Newton-Raphson method? We don't know how much force will be going to each spring. There are springs in parallel, there are springs in series also. So it is much more complex. The interaction between the springs is much more involved. So we may not be able to solve it that easily. Let's use the Newton-Raphson method. So the first step will be to calculate the SFF, right? Tangent stiffness matrix. So we will start with the calculation here when the force and displacements are all 0. So SFF, for that we need to calculate S total first. For that we have to calculate the stiffness matrix of each spring first. So for the first one it is 1 minus 1 minus 1 1. That is between first and second degree of freedom. For the second spring it will be 1 by square root of d plus 1, or I'll take this one out. 1 square root of d2 plus 1. 1 minus 1 minus 1 1. Okay, for the second spring, and this degrees of freedoms are 2 3 2 3. For the third spring, correct, and the degrees of freedom are 1 3 1 3. Everybody agrees with this? Now S total can be calculated from here. Let's put the terms corresponding to 1 minus 1 minus 1 1. That is 1 and 2. 2 and 3 will be again 1 by d2 by 2 plus 1. That is 2 2, then 2 3. And similar thing here, minus square root of d2 plus 1. And the third term will be plus. Now 1 3 spring is still pending, so that will be 2 minus 2 minus 2. So 1 and 3, right? So 1 2 3. 1 2 3. So the term belonging to this one, so plus 2 will come here. 1 minus 2 will come here. 3 plus 2 will come here. And 1 3 minus 2 will come here. Is that okay? I hope I didn't make a mistake anywhere. Fine. So what is SFF now? What are the free degrees of freedom? 2 and 3, right? So this is my SFF. 1 plus this term, minus this term, minus this term, 2 plus this term, correct? So that's what I have calculated. So this is the total stiffness matrix I have calculated, and from there I have calculated SFF, which is 1 plus this term, minus this term, minus this term, 2 plus this term. I'm just calling it this term instead of repeating the whole thing. Right? So I got SFF. Everybody agrees with how I got SFF?
Yes, sir.
Yeah. So, okay. So now that was the first step, calculating the tangent stiffness metric. The second step is to solve it. So unbalanced force was 0, 10 initial force. I have applied 10 kilonewton, right? So that is unbalanced at the 2 free degrees of freedom. What is 0? What does 0 represent here? Why 0?
No external load.
No external load at
second degree of freedom.
At this degree of freedom, there is no external load, so that's why 0. There is no unbalanced force here, but there is an unbalanced force of 10 kilonewton here. So 0, 10 is equal to SFF delta. And from here, we can get the values of deltas. So I solved for delta. Before solving that for delta, we have to calculate the stiffness matrix values. So this is the SFF matrix, but which is having a terms of D2. So having a term of D2 here, right? Which is nothing but delta 3 minus delta 2. In the beginning, in the initial stage, our deflections are all 0. So delta is 0, delta 2 is 0, delta 3 is 0. And because of that, your spring deformation is also 0. Okay, so I substitute the value of D2 as 0, or the difference between delta 3 and delta 2 is 0. And from there, I will get the value of stiffness matrix. That is 2 minus 1 minus 1, 3. And I can solve for delta 2, delta 3, which gives me 2, 4. Yeah, so now second, third. So my deflection at the second degree of freedom is 2. I'll just write it. 2 is the deflection here. 4 is the deflection here. How much is the deformation in each spring? The first spring, what is the deformation?
2, sir.
The first spring, the deformation is 2. Second spring, the deformation is
2.
Third spring, the deformation is
4.
4, sir.
Everybody agrees with this, right?
Yes, sir.
Okay. So for the 3 springs, the deformations are 2, 2, 4. 2, 2, 4. These are the spring deformations. Which step was that? This was state determination. After solving the system, I go into the state determination. State determination requires first me to calculate the internal deformations, then internal deformations to internal forces. So for each spring, the first and the third springs are linear springs. So this one has the stiffness of 1. That means 2 deformation means force is also equal to 2. This spring has a stiffness of 2. That means a deformation of 4 represents a force of 8. Okay, so these two are straightforward. The third one, which was having this relationship between the force and the deflection, I substitute, this relationship between force and displacement. I substitute the displacement value, which is basically 2, and 2 plus 1 is 3. So 2 square root of 3 minus 2 is basically 2 square root 3 minus 2, which is 1.464 approximately. Yeah, since it's a numerical method, you don't have to give beyond a certain number of digits. Okay. Up to whatever level of accuracy you want in your converse solution, maybe 1 or 2 digits more than that is enough. Fine. So you got the forces in each spring. Now, if you look at this system, I got the force in each spring. The first spring is having a force of 2. The second spring is having a force of 1.464. The third spring is having a force of 8. Right? Now we can do the force equilibrium for each degree of freedom. So for this joint, that is this joint, what is the force acting on this one? From the first spring, the force of 2 is acting. From the third spring, the force of 8 is acting. But that doesn't matter, because this can absorb whatever force you are applying. It's a fixed boundary condition. For the second node, a force of 2 is acting this way, and a force of 1.464 is acting this way. For the third joint, 1.464 is acting here, and a force of 8 is acting here. And what else is acting at this joint?
External force.
Yes, a 10 kilonewton force is acting here, right? So there is no imbalance here. This imbalance we don't have to worry about, because this is a boundary condition. This one has got an imbalance. How much? That imbalance is 0.536. That is the difference between 2 and 1.464. At this joint, we got 10 kilonewton acting here, and 8 plus 1.464, which is 9.464, is acting in the other direction. So there is an imbalance of 0.536. You got an imbalance of minus 0.536 here and plus 0.536 here. So these are the new imbalance force. Going to the next iteration, again we repeat the exercise. This time SFF, the new values are given for the new delta values. Remember, the delta value had changed now. For your D1, D2, D3 of 2 to 4, 2, 2, 4. So for this D2 of 2, your values here will change. Now, earlier this D2 was 0. Earlier this value was 0, but now this is 2. So correspondingly, the stiffness matrix will change. So that stiffness matrix has new values now, right? And the unbalanced force we had input plus 0.536 minus 0.536 in that order, minus first and plus first, as it was here. That is the unbalanced force. This is the inverse of stiffness matrix. We have taken the inverse of this stiffness matrix. You don't have to take inverse. You can solve it by any other method. And we get the deflection values. These are the new deflections for the unbalanced force. So the total deflection will be the original deflection that we had calculated in the first iteration plus the new deflection. So total deflection is this much. Okay. Now these are the deformations. So from this is the second step for second iteration. This was the first step for the second iteration. This will be starting of the third step, state determination. So for the state determination, first we calculate the spring deformation from the displacements. We calculate the spring deformations, then we calculate the spring forces, and we again calculate the unbalanced forces, okay, which turn out to be 0.008. We can stop at this time. You can see that the unbalanced forces are very small in comparison to 10 kilonewton force. So what fraction is the unbalanced force of the total force? It is 0.008 divided by 10, right? So it's about 0.08%. It's a very small fraction of the total force applied. We could have called it a convert solution, or you can go one step forward, do one more iteration. Either way, okay? So, but you followed the process, right? So I have in this example one more iteration. There's nothing fancy, and next time you get even smaller unbalanced force, 0.0003. So you can call it a deflection. You can see that in this deflection, in this iteration, you got a deflection of 1.708. In the previous iteration, you got the deflections of even almost the same. No, sorry, 1.7128. After one more iteration, you got 1.708. Okay, slightly different. And 4.14 instead of 4.14, you got 4.1458. So there was not too much of a change from this iteration to that iteration. All right. So I hope you were able to follow the discussion. If you have any questions about the Newton-Raphson method, how it is applied to these spring problems. Similarly, it can be extended to all kinds of trusses, etc. In fact, I'll give you an assignment where you need to use the Newton-Raphson method for a truss problem. Okay. Any questions? All right. So if there are no more questions, I'll stop today. We'll continue in the next class. There is one more example on the Newton-Raphson method, which we will